This is Vector Notes, and what you should do is open up Schoology, find the document titled Vector Notes, and have that open in the background in Notability. Or you can open up your packet to Vector Notes and just take notes right on the sheet of paper there. So get yourself ready to go. You'll also need a straight edge. So you want your note sheet. You need some sort of like a ruler or a straight edge. And that's about it. Okay, so here we go. Alright, on this sheet for vector notes, it says what is a scalar and what is a vector. So let's go ahead and get some definitions down. A scalar has size only, and a vector has both size and direction. So some examples of vector quantities that we've looked at already are velocity, acceleration, displacement, just recently, force. Examples of scalar quantities would be something like speed, would be something like distance, even mass, time. Things where adding a direction really just would not make sense. We don't say it's 4 o'clock north. So that is the difference between vectors and scalars, is whether or not you add direction into the definition of what it is that you're looking at. There are some conventions that we use for directions of vectors, and basically most of the time we're going to be talking about north, south, east, west. So we've got never eat soggy waffles. And if you want to decide which way a vector is pointing, what you're going to do is have an axis at the beginning or at the tail end of a vector. So when you're drawing a vector, you're quite literally drawing an arrow. And just like this arrow right here is drawn, what you can see is that it'd be kind of hard to decide really what direction these are going in or what angle they're at without putting in some sort of a coordinate plane. So at the base of each one of these, what you're going to do, let me see, is go ahead and draw a coordinate plane much straighter than I just did. And that way you can take a look, and if I were to call this north, south, east, west, I would say that this vector is pointed northeast, which means that this vector over here is pointed west, due west actually. Due west means 100% to the west, not at all to the north, not at all to the south. Let's see what this one is. I would say that this one is northwest, and that this one over here is southwest. Now, if we are going to add up vectors, there's a way that we're going to do that. You always have to connect them tip to tail or head to tail. So if you're going to draw an arrow and add another vector to it, you would add it in this type of fashion, where they're all tip to tail. If you take a look and scroll down a little bit to the next part, we will do this example of the two tugboats that are pulling a large barge. So let's say you've got a tugboat, and another tugboat, and they are attached to these ropes, and they are pulling a large barge. So you can picture they're moving in this direction, but that the ropes that are connected are in the direction as drawn, and they're pulling this barge as it goes. Now, if you are taking notes in Notability, you can use a copy and paste tool. But if you're just drawing on your sheet, what you're going to want to do is imagine that you have each of these vectors here that, oops, sorry, I clicked something wrong there. Each of these vectors here that are originally drawn, imagine that you can pick them up and move them because you need to connect them head to tail. So if you're going to do that, I would take the top one and say, okay, it's like this, and then if I were to take that other one and connect it, it would be like this. And so the resultant of those two, if I start here and I end here, would be in this direction. If you add those two together, this would be my resultant. And that would be the resulting direction that that barge would be headed in. And now if you were going to draw this to scale, and we said that 1 centimeter is 500 newtons, the length of each of these arrows that you would draw here would have to represent exactly how many newtons it was pulling at. So you can take right now your measuring tool and measure the length of this line, figure out how many centimeters it is, and then write in how many newtons that represents. So how many newtons is this side? Measure the length of it. And how many newtons is this side? And then what you can do is figure out the net force by just measuring the length of that resultant and setting it to this same scale. You could also use trigonometry if you wanted to find it out that way. So, let's say we're given the resultant instead of the two components that make up the resultant. So now we're given the final net displacement on something, and I want to figure out instead, what two pieces made up this displacement. So what I'm going to do is put in my coordinate plane like so, and I'm actually going to extend it so that it reaches the length of this vector. And what you can do is say, all right, to make this resultant vector, I could add these two vectors together, and that would make that resultant. And so you can measure with your ruler the length of this side and figure out how many centimeters that is. You can measure the length of this side and figure out how many centimeters that is. And if we had a scale for that, then you could figure out how many kilometers in each direction that went. Also, you could use your protractor to figure out either this angle or this angle and use your trig to find those two sides. That's another way. We're going to practice with that as well. Here's another example of a resultant vector that you're given. You can put in your little coordinate plane here, and so we have east and we have south. You could figure out the angle that this is at, and if you were to extend this down and then extend this over, you could say here is my vector component to the south and here is my vector component to the east that made up this resultant vector. Now there's a scale at the top here, that says 1 centimeter equals 30 meters per second. So what I want you to do right now is measure the resultant. That's the original line that was sitting there. So measure the resultant in centimeters. And then tell me how many meters per second is this side. If every 1 centimeter is 30 meters per second, put in the answer to that. Then what I want you to do is measure in centimeters each of the components. So here and here, measure the south component and measure the east component. Tell me the distance they are, and then once you know that, you should be able to calculate what the speed was in each of those directions using the scale above. So try that part out on your own. So basically what I want you to take away from today is that a vector is basically an arrow, and if you're going to add vectors together, you always add them head to tail, or tip to tail is another way to say that. If you're trying to find the resultant of those vectors, you always start where you started and end where you ended, and just put, typically we used a dashed line with an arrowhead to call that the resultant. When you're adding vectors together, if you start with the resultant, you can go ahead and put in a coordinate plane and then drop a line down and drop a line over and say, okay, here are the two component vectors that made up that resultant. So you can either start with the components and find the resultant, or you can start with the resultant and find the two components. Either way works. Two ways to find the answer. You can measure using your ruler and use the scale that is given to find the number, or you can use trig and your trig functions, a squared plus b squared equals c squared, and then all of the trig functions, which we will go over together in class to figure that out. The thing I would like for you to work on now is called the displacement vector worksheet. Displacement vector worksheet. You can find that in Schoology and just add it to your notes. And it's going to ask you things like what direction is each one headed in. So you can put in a coordinate plane and try that out. It's going to also ask a series of questions, and you're going to have to work that out on graph paper. So you're going to want to get up and get some graph paper off the front desk. It's there waiting for you, and I will see you soon.